This is going to be the first section of 9.3 on the double angle identities. So double angle identities are just special cases of your sum formula. So let's remember your sum formula is the sine of alpha plus beta equals, oops, you can't see that, equals the sine of alpha plus the, times the cosine of beta plus the cosine of alpha times the sine of beta. So that was your sum formula for sine. Okay, so then I'm also going to need you to remember that from way back in elementary school, if you had like a plus a, that would be 2a. So you did that when you were learning to multiply. So then what we can see is that if both of these angles were the same, so if this was sine of alpha plus alpha, that would be the sine of 2 alpha, right? So then we could still use our identity. So we could say that then that is the sine of alpha cosine of alpha plus the cosine of alpha sine of alpha. And then we'll just do a quick rewrite using the commutative property, and that's going to be sine of alpha cosine alpha plus sine alpha cosine alpha, just so that we can recognize that those two are exactly the same thing. So now we have the sine of 2 alpha equals 2 times the sine alpha cosine alpha. So that's going to be your first identity for the double angle. Double because we have a 2 right here. So that's your first double angle identity. Okay, so similarly, we could do the same process for cosine and tangent to get cosine and tangent's double angle formulas as well. Okay, so we are going to do cosine because it will take several forms. So the cosine of 2 alpha equals the cosine of alpha plus alpha. Okay, and then our double angle identity for that is, or our sum identity for cosine is going to be cosine alpha cosine alpha minus sine alpha sine alpha. That's just the sum identity for cosine, but both of the angles are the same because we want 2 alpha. Okay, so that is going to give us cosine of 2 alpha equals cosine squared of alpha minus the sine squared of alpha. Okay, we just simplified those. Cosine times cosine is cosine squared. Okay, so then we're going to use the Pythagorean identities to rewrite this in a couple of different ways. So we're going to have the cosine of 2 alpha equals, well, cosine squared, according to the Pythagorean identity, is 1 minus the sine squared. So that would be 1 minus the sine squared of alpha minus the sine squared of alpha, which simplifies to 1 minus 2 times the sine squared of alpha. So that gives us our first cosine, actually our second cosine double angle identity. So this will be the first one. And then now you have cosine of 2 alpha equals 1 minus 2 times the sine squared of alpha. We can also take this and instead of substituting for cosine squared, we're going to substitute for sine squared. So I'm going to get the cosine of 2 alpha equals cosine squared of alpha minus 1 minus the cosine squared of alpha. Because that, if we use our Pythagorean identity, we have 1 minus the cosine squared is the sine squared. So if we simplify this, it's going to be the cosine squared of alpha minus 1 plus the cosine squared of alpha. We just distributed that negative. So that's going to give us the cosine of 2 alpha equals 2 times the cosine squared of alpha minus 1. Cosine squared plus cosine squared is 2 times the cosine squared. So we have 3 different versions of the cosine's double angle identity. Okay? And then for tangent, we just have one. So I'll go ahead and give you that one. So your double angle for tangent is going to be the tangent of 2 alpha equals 2 times the tangent of alpha divided by 1 minus the tangent squared of alpha. And I'll go ahead and give you that identity. Use the fact that tangent is sine over cosine to derive that, okay? But so just like we used our other identities, we can use these identities to find exact values. We can prove or verify other identities, and we can use it to simplify equations. Okay, so for example, if we wanted to find an exact value using these identities, okay, so I'm going to find the exact value. Okay, if I know that the tangent of theta is negative 3/4, I'm given that in the problem, and I know that theta is in quadrant 2, okay? And I want to find the sine of 2 theta. Okay, so that's the problem. That's everything that I was given. So I'm going to go ahead and go over here and do a little triangle. Remember, I'm just doing it randomly. It doesn't really. So if this is theta, I know that tangent of theta is the opposite over adjacent. So that's going to be 3, and this is going to be 4. Now, if you remember your Pythagorean triples, that means this side is 5, because 3, 4, 5 is a Pythagorean triple. If you don't remember that, you just take 4 squared plus 3 squared equals 5 squared and solve. Or 4 squared plus 3 squared is x squared, and then solve for x, and that would give you 5. Okay, so then I'm going to go back here, and I'm going to say, well, I've got an identity for the sine of 2 theta. Let's start with that. So I have the sine of 2 theta, and that is going to be equal to 2 times the cosine of theta sine of theta. Okay, that's from my identity. Okay, so I know that. Then I'm going to substitute my values. So 2, well, the cosine of theta, according to my triangle, is the cosine is the adjacent over the hypotenuse. So it's going to be 4 over 5. Okay, so 4 over 5. In quadrant 2, the cosine is negative, so I have to put my negative there. The sine of theta is the opposite over the hypotenuse, and the opposite over the hypotenuse is 3 over 5. In the second quadrant, the sign is positive, so I can go ahead and leave that positive. So I'm going to simplify 2 times negative 12 over 25. And then I can simplify a little bit more, and I can get negative 24/25. And so the sine of 2 theta, which is what I was trying to find, is negative 24 over 25. Okay, so using this strategy, you should be able to do the end of this chapter, section 9.3, it's on page 730. You should be able to do 5, 7, 11, 25, 29, 31, and 33.